Okay, welcome back. Can you hear me? Okay? No. Okay, so we changed the gain on the mic, so we're going to fix that now. It's pretty high, but okay. Can you hear me now? Is that any better? Bryden's adjusting it as we speak. It's getting better now? Okay. Yeah, yesterday I guess the video was clipping a bit. Okay, so the audio. Right, so today I'm going to, so this is my second lecture. So this, my second lecture is probably the most, I put the toughest lecture second, okay, which is probably good because maybe you're still awake and, can focus to some extent. But as I mentioned yesterday, the third lecture later in the afternoon will be fairly unrelated to this lecture. Okay, so what I'm going to try to do today is prove the main conjecture or sketch a proof of the main conjecture of Iwasawa theory. So for that, I need to explain a few things. Okay. So let's just recall that P was an odd prime, okay, and I had the field F infinity, which was Q mu P infinity, and that was the cyclotomic ZP extension of F, which was Q mu P. And I had some groups, gamma, which was the Galois group of F infinity over F, which is isomorphic to 1 plus PZP. And I had chosen in this a generator upsilon, which you can take to be 1 plus P. And I also had delta, which was the Galois group of F infinity over the cyclotomic ZP extension of Q. And that's a group of order P minus 1. And then I sent that into ZP cross by the composite character we called omega. Okay, so I had this, and this has appeared also a lot in the interim. I had this unramified Iwasawa module over F infinity, the Galois group of the maximal unramified abelian pro P extension of F infinity. And this was a finitely generated torsion lambda module, where lambda is the completed group ring of gamma, which in turn was isomorphic to a power series in a single variable by sending gamma minus 1 to T, where gamma was the group element of upsilon. Okay. So that's just, so then we had the Iwasawa main conjecture, which I stated toward the end last time. So the main conjecture of Iwasawa theory, or Iwasawa, let's start that one over. Okay, Iwasawa main conjecture. Right, so that was if k is even, and let's just assume, remember that it was sort of uninteresting if k was 0 mod p minus 1. Then the characteristic ideal as a lambda module of this finitely generated torsion module in the 1 minus k eigenspace. So remember that we broke up. So if I have an arbitrary, if I have an arbitrary ZP delta module, which this X infinity is, it breaks up as a direct sum of p minus 1 different eigenspaces for powers of the Teichmuller character, and that's one of them. It's one of the odd ones, contributes to the minus part, which is the part that is controlled directly by p-adic L functions. So that's generated by some element fk, which gives you the p-adic L function. Oh yeah, of omega to the k. Okay, so that's the Iwasawa-Main conjecture, and that's a theorem of Mazur and Wiles from 1984, and there's sort of two proofs of this that one often gives. The first was due to Mazur-Wiles, and it's the one we're going to talk about today, which uses congruences. And the second is the method of Euler systems, which appears in Sarah and David's lectures. And yeah, that sort of gives you, they're sort of opposite in a sense, because in the proof we're going to do, we show that the characteristic ideal is divisible by Fk, and the other proof gives you the other divisibility. But in fact, if you prove this for all k, you only need one such divisibility, which is as a consequence of the analytic class number formula. So right. So in general, if you don't have such a formula, then one divisibility will not suffice. But in the setting we're in, it does. Okay. So Ribot's method is, well, what Mazur and Wiles did is sort of greatly extend the method of Ribot used in the proof of the converse to Herbrand's theorem. And his method was to, sort of find an unramified p extension of the, so he was looking at q mu p, right? And he wanted to show that the class number, or the class group, p part of the class group of q mu p, or f, as we call it, is non-trivial if p divides some Bernoulli number. So what did he do? He looked at the Galois representation attached to a cusp form that's congruent to an Eisenstein series mod p, and he found some unramified extension in the fixed field of its kernel. So we have to sort of generalize this, and how do we have to generalize this? Well, we need to look at all such cusp forms of all p power levels at once. So what is the method of doing this? So I guess it was really introduced in Wiles's proof, but you need Hita theory. Okay, so I want to talk about modular forms a bit. So let's think of lambda here as ZP double bracket T. Oh, yeah. It's the Tyche, yeah. Right, so, okay. So lambda is a ZP double bracket T. Right. So there's a lot of similarities between Hita theory and Iwasawa theory. So let me say what a lambdatic modular form is. So I'm going to have to assume you know what a modular form is. Okay, so a lambda-adic modular form, let's say of character omega to the k minus 2 for some k, is a power series. F in the quotient field of lambda plus, so the constant term could be in the quotient field, but in general, the other coefficients should be in lambda. So of such that for all finite order characters, continuous characters of, so finite order, p-adic characters of gamma, and j, well, okay, I should say for all but finitely many, actually, but it's not going to matter for us. J greater than or equal to 2, f of epsilon nu, epsilon upsilon, right, times upsilon to the j minus 2 minus 1. So I plug that in. So now, how do I plug this in? Right, lambda, I plug in for t. Okay? So what happens if I plug in for t? Then I get a modular form. Is a modular form of level p to the r, okay, so for level, right, the level, right, is, if I take the kernel of epsilon, it's going to be some power of gamma, right, because it's a procyclic group. So that determines the R. Weight J, and character epsilon omega to the k minus j. So this will actually be a modular form with some p-adic coefficients in the extension of Zp given by the values of epsilon. But so we can think of modular forms with p-adic coefficients as just lying in the tensor product of modular forms with z coefficients with the ring we're talking about, with the p-adic ring. Okay, so anyway, I should get modular form. So a lambda-adic modular form should give you modular forms of all weights and levels. Okay, or almost all. Let me give you an example. Lambda-adic Eisenstein series. So EK will be, let me call it CK, I'll define that in a second, over 2 plus some, I'm not going to be able to fit this in one line, I think, some n from 1 to infinity, some d dividing n, p does not divide d, d omega to the k minus 2 d times 1 plus t, I'll write log nu d q to the n. So here, log nu is like d omega inverse d is supposed to be nu to the log nu d. So this will lie in 1 plus p zp, and so it'll be a power of epsilon. Okay, so so that, and also I need to say what ck is. Okay, where ck, yeah. Oh yeah, so q of lambda is the quotient field of lambda. Yeah. Oh yeah, here. Mm-hmm. Yeah, I'm listening. Oh yeah. D, so this is d times omega, the character omega to the k minus 2 applied to d, times 1 plus t to this power. And I'm taking the sum, right? That's the coefficient of q to the n. What I wrote to the, oh yeah, sorry. This is defining log nu to the d. Okay. Yeah, this is the end of the formula. Yeah? Yeah. Okay. Right. So so the where comes before this too. Okay. So right. So ck to the ck of, if I plug in epsilon to the s minus 1, I get the p-adic L function. So I had several of these functions at the end of last time. I think I had s, minus s, and 1 minus s. Well, now I have minus 1 minus s. Okay, for all s and zp. Okay. So what happens if I specialize this? Let's just forget the finite order character, and I specialize this at, say, epsilon to the j minus 1, where j is greater than or equal to 2. Then I get Eisenstein series of level p and weight j, which I won't define, but so this is level p, weight j in character omega to the k minus j. So it sort of p-adically interpolates all of those nice Eisenstein series. Gives you a family of Eisenstein series. Okay, so what's a cusp form? A cusp form is something that, if I take all of its specializations here, they're all cusp forms. So F is a cusp form if all of its specializations are. Okay. Now, the problem we have with the spaces, we could consider now lambda modules of lambda-adic modular forms and lambda-adic cusp forms, but they're too big, and we don't have good control over them. So what we do is we cut down the size of these spaces by applying a certain idempotent, which comes from the UP operator. So we have a UP operator on M, which is the sort of lambda-adic forms, and it preserves the subspace of, oh, actually, I'm just going to use this S, lambda-adic cusp forms. Right? And what does it do? If I look at the nth Fourier coefficient of, or the nth coefficient of AN, the nth Fourier coefficient of UPF, this thing is just the nth coefficient of F. Okay. So we say if I have an eigenvector for this UP operator, meaning it just multiplies by some element of lambda, then we say it's ordinary if that eigenvalue is a unit. Okay, that would be an ordinary lambda-adic modular form. And it turns out that there's an idempotent that projects us onto the ordinary forms. So it'll get rid of the ones that are eigenvectors but not ordinary, where the UP coefficient is not a unit. So let me write down, so this is Hita's idempotent. It's a very strange looking thing, but it's pretty neat. So it turns out that this thing converges as an operator on the space of lambda-adic modular forms. You take the limit as n goes to infinity of UP to the n factorial power. And this projects onto sort of ordinary parts. So let's just declare, so M ord to be E applied to M, and S ord to be E applied to S. And, you know, if I could expand my coefficients so I have a basis of eigenvectors for UP or something, then, well, then this thing is going to be spanned by, the M ord will be spanned by eigenvectors where the eigenvalues, the pth eigenvalue of each F is a unit. So maybe F, yeah, I didn't leave myself no space. Eigenvector is ordinary if APF is in lambda cross. Okay? Great. So those are my spaces of lambda-adic, ordinary lambda-adic forms. Yeah. Did I get it wrong? Oh, what is the character of the Eisenstein series itself? K minus 2, I think, probably. Or K, I think the D needs to be there, yeah. Well, let's not worry too much about what the character is. Okay. Great. Okay, so the theorem of Hita is that these are these ordinary spaces of ordinary lambda-adic modular forms are finitely generated free lambda modules. Okay, so it's very nice. And we have, we actually have Hecke algebras. Inside their algebras of lambda linear endomorphisms, which I'll denote sort of by H's. So these are lambda-adic Hecke algebras. So they're generated by the Hecke operators, which I didn't define, but they're Hecke operators and diamond operators, and they act on these things. Okay, so we have one acting on the modular forms and a smaller one, which is a quotient, acting on the cusp forms. Okay, so he'd proved a duality theorem. And that is kind of, actually it works for modular forms, just with any coefficients, which is quite nice. Don't have to do lambda-adic. But so it's good to know, even in the context of finite level. Okay, so there are perfect pairings like this. And what is the pairing? So perfect pairings. Yeah, so what is the pairing? If I have a Hecke operator and I have a lambda-adic form, I can let the Hecke operator act on the lambda-adic form, and then I can look at the first Fourier coefficient. So if t were, say, Tn, and f were an eigenvector for Tn, this would be the nth Fourier coefficient. But this, yeah, this turns out to be a perfect pairing in both cases. Okay, so the really nice thing, as I said, you don't have good control over lambda-adic modular forms in general, but you do for ordinary lambda-adic forms. So we have control theorems. Works for Hecke algebras, so it works for all four of these things I've now defined. Oh yeah, so I need to tell you what omega kr is. Yeah, there's a commutativity, and yeah, so I didn't say in what sense this commutes, but if I have a if I have a Hecke operator here, and I have a cusp form here, I could restrict the Hecke operator to acting on cusp forms, and then I pair, and that, right? Yeah, it's compatible. Okay. Okay. Right. So I have control theorems for. Oh yeah, p to the r, zp, ord here. Okay, so I can apply my my idempotent at any finite level as well. So I can take an ordinary part of this. So these H ords, yeah, at finite level I have a Hecke algebra here and I apply an idempotent. That gives me an ordinary part. I can also do this for modular forms. So I haven't defined this notation, so I should do that. Okay, so omega kr is 1 plus t p to the r minus 1 minus upsilon p to the r minus 1 k minus 2. Okay, so that's an element of lambda. So I take the quotient of my Hecke algebra, my ordinary Hecke algebra, by this element. I recover the weight k Hecke algebra of level p to the r. That's what that means. Weight k level p to the r. So the important thing to get out of this is we get ordinary parts of modular forms and Hecke algebras of all weights and levels. We have this sort of perfect control just by taking this quotient. Oh yeah, here no, epsilon here is a number. Yeah, and there it's the variable, right? So it's not the group element here. You see, t is the group element minus 1, so it's an element of the group algebra, right? This is the element of the power series ring. This is just a number in 1 plus p, zp. Right. Yeah. So it's a coefficient. Okay, yeah. So we recover from these Hecke algebras, ordinary Hecke algebras and ordinary modular forms, right, all weights and levels in the ordinary part. Okay. Okay, so one more thing. We need Galois actions, right? I said we have to do some, right, we have to have some Galois representations. Where do Galois representations of weight 2 come from? They come from the tau cohomology. So that's one way to think of it. Okay, so this thing has an action of the Hecke algebra that I was just defining, weight 2, level p to the r. Same Hecke algebra that acts on the space of modular forms. Right-hand side of what? Yeah, that's the Hecke algebra of weight k, level p to the r, acting on the space of modular forms with ZP coefficients, and take ordinary part. Right. Okay. So this also has a commuting action of the Galois group. Yeah, this is over Q bar. Okay. Yeah, so right now this is over, this should be considered over an algebraically closed, over Q bar. Okay. Oh yeah. Let me write that here. Also for cusp forms and cuspidal Hecke algebras. Classical definitions. Right. Well, okay, but with ZP coefficients. But that just means you take modular forms with Z coefficients and you tensor with ZP. Okay. Okay, so great. So we have these are commuting actions. We have a commuting action of the Hecke algebra. This is actually the dual action or the adjoint action. So you transpose your correspondences. But I'm not going to worry about that. That's the action we need here. And here, this is Galois, the 2 commute. And they're also compatible under trace maps as I go up the tower. So I can take an inverse limit of these tau cohomology groups, much as I was doing, as I could do here. But to have good control over this, again, I need to take ordinary parts. So let me just define T ord, we'll start with ordinary parts, to be the inverse limit of these things, these tau cohomology groups, ord. So what can I say about this thing? Okay, so here's a theorem, let's say of Hida and Ota. Okay, so parts, the general form here is Ota. So T ord has, it's a Hecke algebra over my ordinary cuspidal Hecke algebra. It has H ord rank 2, but it's not necessarily free. That means if I tensor with the total quotient ring of this, it becomes free. And actually, if I tensor with Q lambda, it becomes free over H ord tensor Q lambda. But it is free over lambda of finite rank. And moreover, there's an exact sequence of modules for, if I look locally, this is what, so this is the key about ordinary representations. It doesn't just tell you something about, it also tells you something about the form of the representations. And I think this was mentioned in a previous talk. And that is that we get an exact sequence. So we have some submodule, which I'll call sub. And we have some T sub. We have some quotient module, which I'll call T quo. They're both rank 1. Okay? So I can think of these things as somehow giving me my 2 dimensions when I'm doing a 2-dimensional Galois representation. Okay? Right. So if I think of these such that on inertia at P, actually they have this very nice structure. As a Hecke algebra, a Hecke module, this thing is just isomorphic to H. It has some sort of twisted Galois action that we saw last time. So this means Galois element corresponding to J acts as diamond operator J inverse on the H ORed iota. Diamond operator J, sorry, actually. Okay. So it has some twisted Galois action, but as a Hecke module, it's just H ORed. And T quo ORed is isomorphic to the cusp forms. That's where you may not have freeness. Okay. But it has trivial action of inertia. Okay, so some remarks on this. One is that if I look at the GQ action on T, I can think of this as giving me a Galois representation to GL2 of, let's say, the quotient field. Right, so the Hecke operators act on the tau cohomology, so I can apply Hita's idempotent to this, and I get ORed. Yeah. Okay, so right, and that's actually what tells you that the fact that I've taken the ordinary part actually tells you you have this sort of exact sequence. Okay, so I get a 2-dimensional Galois representation, and if I choose the basis where this is like the first variable, T sub, and T quo is like the second variable, then what's it going to look like on inertia? Rho on inertia at P is going to look like the determinant 1, 0, star. In fact, it's upper triangular, but there may be some unramified character in its inverse here on decomposition. And so, and what's the determinant? I mean, the determinant on a Frobenius at L is actually going to be L diamond operator L for L not equal to P. So I can think of this as an element of the Hecke algebra. There's a diamond operator, and so it lies in the Hecke algebra. And the trace, very interestingly, is just going to be the Elf Hecke operator for L not equal to P. So this thing sort of parameterizes Galois representations, ordinary Galois representations, again, of all weights and all levels. So this is Hita's theorem. Yeah. Yeah. Well, I mean, I think what I gave is about how I can describe them for now. Yeah. So this. Yeah. So this thing has an inertia subgroup at P, and then as modules over the group ring of the inertia group, we have these isomorphisms. Right, no, but they come from p-adic Hodge theory. Yeah, but, yeah. Uh-huh. That's S-ord. Yeah, so that's the lambdatic ordinary lambdatic cusp forms. I think yeah, here. Define, yeah, this, there, yeah. Okay. Yeah. Elf Hecke operator. Yeah. Okay. So now so the second remark is that sort of if I take T-ord, let me just do this in weight 2. I mod out by omega 2r and I take T-ord, okay? Then I'll get H1, X1, P to the R, ZP1 ord back again. Right. So, let's check the time. Okay. So, so I have this good control in weight 2. And in fact, it works in all weights, but I didn't tell you what the Galois representation is in higher weights. Okay, so I get every level in weight 2. So I have this sort of perfect control. Right. Right. And how do I get maybe I should say how I get a Galois representation attached to a cusp form, right? Okay, so if I have a cusp form, so say a new form of level P to the R, okay, then I have a map, Pf, from my Hecke algebra to the field QP bar or the field of coefficients, but let's just say QP bar. Field of coefficients will be finite degree over QP. And I could look at the kernel of this thing. Okay? Now I could take the quotient of this thing by the largest quotient where this kernel acts trivially. And I could tensor that with QP. So this thing actually becomes a two-dimensional vector space over the field of coefficients of my modular form. Yeah, ordinary. Okay. So they call this VF. So VF is two-dimensional over KF equals, I don't know, QP adjoin all Fourier coefficients of the F. Right. So, yeah, so this is how I sort of recover the two-dimensional representation attached to a weight 2 cusp form. And so we get the Galois representation for all weight 2 cusp forms as quotients of this T-ord. Okay, so let me now mention another ideal where you have called the Eisenstein ideal. This one doesn't come from a cusp form. It comes from the Eisenstein series. So this thing, phi-f, I defined over here, was a ring homomorphism. Okay, exactly because this is a new form. Well, the Eisenstein series, right, so will not give you a homomorphism from the cuspidal Hecke algebra to ZP because, well, it's not a cusp form, but does give you one from the full modular, the larger Hecke algebra. But I'm actually interested in the ideal the coefficients generate in this smaller Hecke algebra. So let's take the ideal IK to be the ideal K is even, generated by TL minus 1 minus L diamond operator L for L not equal to P, UP minus 1. And then diamond operators should act as omega to the k minus 2 of j if j is in Z mod PZ cross. So if you like, these 1 plus L character L were what appeared as the Lth coefficients of that Eisenstein series I wrote down. The 1 would be what appears as the Pth coefficient. So this thing is given by Hecke operators minus coefficients of my Eisenstein series. And you sort of get all of them from these prime ones. So, okay, so here's a theorem. So let's consider H board as a lambda module by, I don't know, some number, well, what does gamma act as? Gamma acts as diamond operator nu inverse. So I kind of want to invert the lambda action for some strange reason later. So this is the inverse of the one you might think that's natural. But then it turns out that H ord mod IK is isomorphic to lambda mod, here's my fifth one of these things. CK of nu to the S is, so this is just, I have to switch, I had 1 minus S because I did this thing where I switched the action to its inverse. I just have to change 1 minus S, 1 minus S to S minus 1. Or minus 1 minus S to S minus 1. So this is a theorem of Mazur-Wiles. As a consequence, actually, they proved it as a consequence of the main conjecture. But Emerton gave another proof which doesn't use the main conjecture. And I think that's nicer. So the point is that because the Eisenstein, so where do we get this from? The point is the Eisenstein series constant term was the CK, which is essentially this CK. And so when I reduce the Eisenstein series mod CK, the constant term becomes 0, right? Because that is the constant term. So then it starts to look like a cusp form. So how is that reflected here? It tells you you have essentially a cusp form, but now its coefficients lie in this quotient ring. So actually you have still a ring homomorphism from H ord to lambda mod the quotient ring, from H ord to lambda mod the quotient ring. And the kernel of that is this Eisenstein ideal. And then you have to show there's not just a surjection, but it's an isomorphism, and that's sort of the whole trick. That's where you need the main conjecture or some other trick. Okay, so, right. So now we get to the idea of the proof, I guess. Okay, so let's let M be the MK be the maximal ideal of H ord containing IK. There's one. I can tell you what it is. MK is IK, and then I throw in P, and I throw in a diamond operator of epsilon minus 1. That's what it is. Okay, so I could localize my Hecke algebra. Let's call this H, which will be, we could also call it HK, but the point is it'll be this H ord localized at my maximal ideal. It's a complete ring. It's a direct factor of H ord. And we have T, which I could also call TK, and this will be the resulting module over this localization. Okay, and so this thing, T tensor lambda Q lambda, as I was mentioning, is sort of free of rank 2 over H tensor lambda Q lambda. Okay, so again, we get I'll just repeat what I said before, we get a Galois representation. We think of GQ as H linear automorphisms of T. And this thing, if we choose we can view this as acting on T sub plus T quo, which will be the sub and quotients of this of this localized thing. Okay, and remember again that that on inertia, it's going to look like determinant B1, 0. And so in general, I mean, we can write it as an A, B, C, and D. Okay? Now, the point is now that we've localized at this Eisenstein component, the resulting Galois representation, of course, it's irreducible, but it's not residually irreducible. Residually, it's reducible, and that comes from this congruence. That means if I choose two different lattices in my Galois representation, the residual representations may be non-isomorphic. So in particular, if I take this thing T, it's more natural to consider mod I than mod the maximal ideal here. If I consider, T mod IT may look like, if I don't know what this lattice is, so this is some lattice, right? T is just one choice of many possible lattices. It may look like, just a priori, det star 1, or it could look like this. It turns out the diagonal do always look like this, but or something else. But we don't know, so where we might have a non-zero thing here or a non-zero thing there. It depends on the choice of lattice. So the key to proving the main conjecture is to choose the right lattice. Okay? Okay, so we choose the right lattice. How do we do that? Okay, so we have these maps B and C. Let's declare B to be the span of the image of B. And let's declare C to be the span, this is the one we'll really need, of image of C. So here's some facts. Remember, we can think of this as lying in the GL2 of the quotient field, if you like, or GL2 of this thing even, the Hecke algebra tensor Q lambda. Well, so if I take anything, A of, say, some sigma minus the determinant of sigma, that lies in my Eisenstein ideal. If I take D of sigma, so I was already kind of saying this here, how it might look like. That D of sigma minus 1 lies in the Eisenstein ideal. And also, any B of sigma C of tau lies in the Eisenstein ideal. So you can prove this by looking at how Galois acts on sort of Frobenius, what happens on Frobenius elements and on a complex conjugation. So, okay, so you have those interesting things. That tells you something about what the residual representation looks like. So let's consider C bar, which is C mod I. Okay? Yeah, I is the same as IK. Let me declare I to be IK. Split up when I take the quotient? Yeah, that's from the residual. Well, okay, you could actually have a non-zero star here and here. But the point is it's going to be residually reducible. So it's not going to be an irreducible representation anymore. And that's because of this congruence with the Eisenstein series. You might think that the Galois representation attached to the Eisenstein series is somehow just a direct sum of two characters. And somehow because we're congruent to that, we get some, when we Merck mod the Eisenstein ideal, we have residual reducibility rather than irreducibility. Right. So the key thing we have here is that we do know that B of sigma C of tau is an I. And that's very useful in the sense that, well, here's the claim. So we C bar, right, is going to map GQ to C mod IC. Whatever the module C is, right? We reduce it mod I. So sigma and tau are elements of Galois. Any elements of Galois. So GQ is the absolute Galois group of Q. Okay. So, okay. So here's the claim. phi c, which is the determinant of rho, I have to inverse times c bar, is a 1 cocycle. Okay, well, let's prove that. Okay, so C of sigma tau, you'll believe me, I hope, if I say C of sigma tau is C of sigma B of tau. And if I'm wrong, then you'll D of sigma C of tau, right? Okay, so now we use these facts. That's a C. Sorry, C of sigma B of tau, D of sigma C of tau. B of that's wrong. Yeah, correct this. A of tau should be here, right? What is the correct statement here? Yeah, this is definitely wrong. Okay. Somebody? Yeah. Okay, great. This one's right. Yeah. Okay. A of tau. Right. So, well, we use A of sigma minus, A of tau minus det rho of tau is an ik. So we can replace this. Mod ik, right, this is going to be C of sigma det rho of tau. And D becomes 1. So this is C of tau mod ic. Yeah, I need a couple extra minutes. Okay. So, no. Okay. Right. So this, you see now if I multiply, this almost looks like the cocycle condition. If I multiply by the determinant inverse, now it's the cocycle condition. So this gives that phi c is a cocycle. Psi c is a cocycle. Okay. So determinant becomes trivial if I restrict to the Galois group of Q mu p infinity, or F infinity. So this gives me a homomorphism on G Q mu p infinity. But moreover, remember what was the form of my Galois representation on inertia? What's C? C is 0 on inertia at P. But also, and maybe I didn't write this, my Galois representation is unramified outside P, meaning the only prime that ramified was P, but clearly it doesn't ramify because in the C, because this is 0, right? It's trivial on inertia. So that means, of course, now C is a homomorphism. So psi C is now a homomorphism from G Q mu P infinity to C mod ic. And by construction, it's surjective, right? Because C was the span of the image. You have to check that, okay, it remains surjective at the level of F infinity. But we have this homomorphism. And now it's unramified everywhere. Well, what does that tell you? That tells you it factors through, well, it's going to factor through the maximal abelian quotient. It's going to factor through the maximal abelian pro-P quotient because this is an abelian pro-P group. Okay, but it's also going to factor through the maximal unramified quotient. That means it factors through x infinity. So we get a map like this. And it's surjective. See, so we've already constructed some non-trivial unramified extension in x infinity. So then you have to check. Okay, I don't have time to do this, but you have to check what the Galois action is. So, so actually, and you can check this again by similar computations to this. And so then we just need to ask, how big is this thing? And we can make it, if I twist by 1, it becomes a homomorphism of lambda modules. Where I'm using the inverse diamond operator action here, and I'm using the Galois action here. I had to twist by 1 just to get the actions straight. Okay, so then here's the rest of the proof. C is a faithful H module, which you can see, one can see. And what this tells you is that C mod IC, right? Well, okay, so you don't see this directly. You have to do some argument using fitting ideals, but anyway, I wasn't going to do that anyway. So C mod IC, you could ask, what is its characteristic ideal as an H mod I module, or as a lambda module now, right? It's also a lambda module, and it's a torsion lambda module because it's a module over H mod I, which was a torsion lambda module. So what you get is that the characteristic ideal of this thing is divisible by the characteristic ideal of H mod I, which was just C. This C I wrote before, CK. Okay, so this thing's divisible by C. But this is a homomorphism of lambda modules, right? So this tells you that characteristic lambda x infinity 1 minus k 1 is divisible by C. Okay, but there's this one twist here. So if I account for that, that tells you that characteristic ideal lambda, remember there was a S minus 1 in the definition of C. And that was the difference between C and F. So this was F. So C is CK. Here's F, divisible by. And again, you have, it comes from, what you can prove actually from the analytic class number formula is that the sum of the degrees of the, or the sum of the lambda invariants, or the degrees of the distinguished polynomials dividing Fk, is equal to the sum of the lambda, the ZP ranks of these odd eigenspaces. And so since you know that the sums of the ZP ranks are the same, if you have divisibility for all k, you actually get equality. So divisibility for all k, even, equality. And so that gives us the Iwasawa main conjecture. Okay, so that's the sketch of the proof. Okay, so yeah, so next time I'm going to talk about something different. Maybe in the fourth talk I have to come back a little bit to refine this slightly. But okay, thanks.
Okay, so first, a question. Does anyone happen to have some aspirin or Tylenol handy? Yes. Okay. Can I have some? Oh, really, it's for Sarah, but okay.
Oh, no, that's allergy.
Second, are there questions for Romyar? Yes, okay.
So in the final proof, you're going to use the fact that H ordinary quotient by IK is isomorphic to lambda quotient out by the psi of K?
Yes.
And this, I thought you mentioned that this was a consequence of...
Oh yeah, Maser and Wiles proved it as a consequence of the main conjecture. But in that case, you still have surjectivity, so you still have divisibility by CK.
I see, so you don't really need the full equality.
Right, right. But actually, Emerton later proved it without using the main conjecture, fairly much simpler proof. So.
Other questions?
So what's the action of Galois group on the C?
The action of the Galois group. Yeah. Well, okay. So here so I can tell you that, but here as a homomorphism of lambda modules, I'm not taking the Galois lambda module. So there's two lambda module structures. Yeah.
Actually, one foot cycle, we need the action of the Galois group.
Oh, right, on the C. Yeah. So the Galois action on the C is through so a Galois element corresponding to some number j in ZP cross acts as diamond operator j times cyclotomic character of j. It's the action I described on inertia for the sub part, but it works on the full Galois group on this thing. Yeah.
You made a remark that that T mod ij may look like this this not splitting, but a factor a sub and a quotient. And I guess why was that? Why was that splitting the same as when you restrict to inertia? So
I'm not sure I understand. So
go back a few. Yeah. So just the next. Oh. Okay.
Can you repeat whatever his question is if he doesn't want to use the microphone?
I didn't. Yeah. So
Okay. One page back.
yeah. One page back.
Yeah. So why does T mod ij?
T mod IT.
T mod it. Yeah.
Yeah.
What do you mean it may look like that? And what's this comment? Why is it the same as
Oh.
rho
Okay, so
restricted to inertia?
there are many choices of lattices, right? So here I just say take a lattice. Don't pretend it's not this T, right? Okay, so that's the first thing, right? What's another choice of lattice? I could take the Italic homology of Y and apply a Manin-Drimfeld splitting over QP. I get a sort of larger lattice. There are different choices of lattices. And in fact, somehow in the proof here, I didn't really use this lattice. I kind of replaced this lattice with T-quo direct sum C. Okay, that's the first thing. That's to make this thing non-zero. That's to make this thing non-zero. But depending on the choice of lattice I get, when I reduce it mod I, right? So I choose a lattice, say L. I reduce it mod I. There's different forms that the Galois, if I choose a different L, I may get a different Galois representation mod I. Okay, it doesn't have to look at like this upper, oh, you're asking why it looks exactly like this upper triangular or lower
Why
triangular?
is it invariant subspace, for instance? Yeah.
Right. Yeah, I didn't really explain that. Yeah, you may have to change the basis for this to be true. But in fact, for T mod IT, it actually looks like this one. I mean, that's a theorem. But yeah. Right. So this is just to give you the idea of what may happen, right? With respect to some basis, it's going to have to look like one of these things. Or, I didn't say this was all options, right? These both could be non-zero. Yeah, but their product, again, should be 0. Yeah, maybe we could talk.
Why should it? Okay.
Yeah. Oh, that's because this BC is in I. BC is in I.
All right, maybe in view of the time, let's limit other questions to later over the break. We'll take a 25-minute break. Thank you.